On the worksheet called In-Class Lack of Conservation that we went through and we worked through this first problem together on Tuesday in class, we're going to look at the third one. So the third problem says a 10-kilogram baby is in their baby sled moving slowly at 2 meters per second at the top of a 15-meter tall frictionless hill. If you give them a 10-Newton push for 2 meters, how fast will they be moving at the bottom? Hint, don't worry, they have a helmet on. So they might be going a little fast, but that's okay. They got a helmet on, so we'll be good. So, taking a look at a problem like this, the first thing we have to kind of ask ourselves is this a one location or a two location problem? And we're talking about a baby at the top of a hill goes sledding. How fast are they going at the bottom of the hill? We're comparing the top of the hill to the bottom of the hill. Hopefully you realize and you see that it's a two location problem. So we have our 10-kilogram baby in their sled, which is initially moving at 2 meters per second at the top of the 15-meter high hill. We're trying to calculate how fast are they going at the bottom of the hill. The baby wasn't moving very fast, so you give them a push, which I would consider to be an applied force, and that applied force is of 10 newtons. Now typically, if you give someone a push on a sledding hill, you do not push them the entire length of the sledding hill. So based on that, and what it says you give them a push for 2 meters. Okay, you give them a push for 2 meters, and only 2 meters of that hill. So the hill is 15 meters high, and the baby's going down, in my case here, a hypotenuse. But we're only pushing him for 2 meters out of the entire length of the hill. The thing about this problem, just to kind of put this out there, is this is what we refer to as an incline plane problem. The hill is like an incline, right? This happens to be a frictionless hill, so no problem there. But if I were to say there was friction, we get into some slight complications because in order to calculate the force of friction, we need to know the normal force and mu, which you could say, well, that's not too bad. Yeah, except for on an inclined plane, the normal force always acts perpendicular to the surface, and in this case of my inclined plane, it is at some angle, and gravity is always straight down. So the gravitational force and the normal force are not equal to one another, and we'd have to do some trig functions. So I would not ask you to calculate the force of friction on an inclined plane. Now I might say you push a kid down the hill and there's a force of friction of insert some number, and the hill is 15 or 20 meters long, then that friction acts over the entire 20 meters. That's fair game. Or I might say something, and if you look at this next problem, we aren't going to do this next problem today. This problem is identical with the exception of, on the second line it says, and they lose 1,467.3 joules of energy due to friction. I'm giving you the work done by friction, and that's how much energy is going to be lost. So, just some things to keep in mind. So it's a two-location problem. Because it's a two-location problem, we should be looking for some two-location stuff like V's at location 1 and location 2, H's at location 1 and location 2, and spring stuff at location 1 and location 2. So if from here to here is 15 meters, that'd make it really nice if we call that 15 meters as long as we define the lowest point on the hill, or the bottom of the hill, to be 0. And if we define the bottom to be 0, then my H1 does equal 15. It's a two-location problem, so work in plus the work done by friction is equal to our change in mechanical energy. If it was no work in, and if there was no work done by friction, then it'd be one of those ME1 equals ME2, conservation of mechanical energy. However, It's not. Is there work being put into the system? Yeah, because there's an applied force and a displacement, then we have some work in. Is there work being done due to friction? No, because it says it's a frictionless hill. So because it's a frictionless hill, there is no work being done by friction. And then we can say work in is equal to ME2 minus ME1. And then we can expand out all of our energies and say work in is equal to bracket PEG2 plus PEE2 plus PEEUs plus KE. Bracket minus bracket PEG1 plus PEE1 plus KE1. These three energies added together are ME2. These three energies added together are ME1, and it's minus the sum of those three. Order of operations is important. So you're going to subtract the sum of those three energies. To simplify the energy part a little bit, we can go through and we can ask ourselves questions. Is there a height? Is it moving? Is there a compressed spring at location 2? Is there moving? Does it have a height? Is it a compressed spring? Is it moving at location 1? If we answer no to any of those questions, then we can cross it. So at location 2, we said it's at the bottom of the hill. At location 2, we didn't reference any spring because there isn't a spring mentioned. But it is moving at the bottom of the hill. We just don't know how fast it's moving at the bottom of that hill. At the top of that hill, there is a height, there is no spring, and in this case, the baby is moving at 2 meters per second. So, before we get going too far, we're going to have to start plugging some numbers in here pretty quick. I personally like to calculate work in and work done by friction separately. In this case, there is no work done by friction, but there is work being put in because there's an applied force and a displacement. Now, if the baby's moving down the hill, and if the baby's being pushed down the hill, then our displacement of 2 meters is in the same direction as my applied force. And our work in is going to be a positive because it's going to add energy to the system. We're going to make the baby go faster. We're adding energy because we pushed the baby. So our applied force is 10, but we only pushed the baby for 2 meters. But that's going to cause us to add 20 joules worth of energy to the baby. We're going to add some energy to the baby. In this case, all the mechanical energy on the bottom is in the form of kinetics, so we're going to make the baby go faster. So when we get to this next part, going back to our 2 location problem, I know this number, so I'm going to add that number on the next line. But I go through and I say, well, kinetic energy. In order to calculate kinetic energy, that's 1/2 the mass times the velocity squared. And since we're talking about kinetic energy at location 2, this is going to be the velocity at location 2 squared. And final minus initial is important. Because if we have a positive work in, that means we have more mechanical energy at location 2 than what we started with. Then that's going to be minus, notice I'm using brackets here, m times g times h1 plus 1/2 mv1 squared. If you didn't use brackets and you just plugged in numbers, or if you just wrote it like this, you would subtract this, but then you would be adding kinetic energy, and that's not what this is. You're adding order of operations, brackets, parentheses, you're adding these 2 numbers first, and then you're doing that subtraction. We already determined our work in, which is positive 20. 1/2 times the mass of the baby, which the mass of the baby was 10, times V2 squared, minus the mass of the baby, times our gravitational acceleration on Earth, times the height of our hill, which was given to be 15, plus 1/2 the mass of the baby, times the velocity of the baby, 2, at the top of the hill, and then we got to square that. That, oops, got to close my bracket, is what this looks like prior to doing any of the algebra. Before you write down those last two numbers, let me double check them, but I think they're right. Yep, they're good. Okay, so I go through and I do the multiplication. 1/2 of 10 is 5, V2 squared. Minus bracket. 10 times 9.8 times 15, I have to do the multiplication before I do the addition within that bracket, so that's 1,470, and 1/2 times 10 times 2 squared is going to be 20. It's a bracket, so I got to do what's inside the bracket first, so that I got to add these two numbers together. So that's going to be 20 is equal to 5 V2 squared minus 1,490. Now, just before I kind of do some, can I combine these two terms? Can I combine this term with this term? Why not?
Different variables.
Yeah, they're not like terms, they're unlike terms, they have different variables, right? This has a V2 in it, and I intentionally used red. This has a V in it, this does not have a V in it. Does this have a V in it? No. So are these two like terms? Yeah, those are like terms. So how do I get that 1,490 to the other side? I gotta add it, right, because there's that minus sign. So I gotta add it over. So that ends up, we add that to this side, we end up with a positive 1,510 is equal to 5 V2 squared divided by 5 divided by 5. That's 302, I think. Is 302, which is equal to V2 squared. That's not my final answer because I still need to take the square root of that. So I take the square root of both sides to get us a final answer of V2 equaling 17.38 meters per second. And you can say, is that really fast? Yeah, it's like we're right around 40 miles per hour. But don't worry, the baby has a helmet on, so the baby's fine. It's safe, perfectly acceptable. Child services should not need to get called for a 40 mile per hour sledding trip because the baby has a helmet on. Safety first. Okay. Incline plane makes the friction part a little bit tricky, but the idea is we can go through, and this happens to be a frictionless surface, but there was some work in because they pushed the baby down the hill, so we added some energy to the system. Okay, so we added some energy to the system. Questions on that one? I could if I just make up a number, and if I said from here to here was 20 meters, and if I said that there was friction, and I give you some number of 2, say, I could then say, well, now there is some work done by friction. But the work done by friction has times the displacement. So if from the top of the hill to the bottom of the hill is 20 meters, from here to here is 20 meters, and the baby gets pushed, apply force of 2, when I calculate the work done by friction, we need a displacement. Is friction acting for these 2 meters or the entire 20 meters down the hypotenuse of the hill? If you go sledding and there's friction, is there friction the entire length of the hill or only when the person is pushing you? Right, so keep that in mind, that if we were to say, oh, it's a 20-meter long hill, the hypotenuse is 20, the work done by friction would be times that 20. Not times 15, not the height of the hill, not times 2, not the distance that they were pushed, but for the entire length of the hill, or the sledding length of the hill, the hypotenuse in this particular triangle. The next problem, if we were to do it today and we're not, I simply am giving you this number. So work in, we lose some negative, some amount of work done by friction, we're going to lose some energy. Friction slows us. Okay, so this is on the worksheet called In Class, Lack of Conservation. That was the third problem. Any questions? We're going to do one more today and then we'll move on to something else. All right, I want to go through the second problem on that same worksheet called In Class, Lack of Conservation. On the worksheet called In Class, Lack of Conservation, the second question listed says a 7-kilogram crate is accelerated horizontally from rest by a 40 Newton force for a distance of 2.5 meters, and the coefficient of friction is 0.2. What is the final velocity? It is a 2-location problem. In terms of adding steps to a problem, this is about as many as we possibly could. So realize there's a lot of steps to this problem, but it's about as complicated a problem as we can create. So it's a horizontal surface, so we do have that going for us, which I guess is one thing. We have a 7-kilogram crate on a horizontal surface that's being pushed, but there is a coefficient of friction. So is there friction then if there's a coefficient of friction? Yeah, there's going to be friction. So friction does exist. It's a 2-location problem, and the crate is accelerated by rest, is pushed with a 40 Newton force for a distance, a delta x of 2.5 meters. The idea is right here is location 1, and right here is location 2. At location 1, we're going to want to know what V1 is. At location 2, we're going to want to know what V2 is. That's actually what they're asking us to solve. At location 1, we should know H1. At location 2, we should know H2. At location 1, we should know if there's any springs. There's no any springs. And at location 2, we should know if there's some rest springs, and there aren't any rest springs. Okay. So let's kind of take care of that really quick. What's my V1? Because it says it starts at rest. V2, unknown, we're solving for. If it's being pushed along a horizontal surface, it means flat. Our H1 and our H2, we can say are both equal to 0. This is a 2-location problem. Because it's a 2-location problem, it's a work in plus the work done by friction is equal to our change in mechanical energy. Before we expand out the mechanical energy piece, let's ask ourselves, is there work in? Is there an applied force over a displacement? Yes. Is there friction and a displacement? Yes. So therefore, work done by friction also exists. Both of these things need to stay, just so we kind of know that. Up to you kind of what the next step is. Since I just determined that those two works exist, I like to calculate those two kind of separately. And I can look at my formula sheet and say, hey, the work in is equal to plus or minus the applied force times our displacement. Our work in is equal to plus or minus our 40 times 2.5. If my applied force is to the right, and if this is location 1, and this is location 2, that means our displacement and force are in the same direction. We're going to add them. So then we can say 40 times 2.5. The amount of work being added is equal to 100 joules. We're adding 100 joules worth of energy by pushing this crate. I said, you guys helped me, I think someone told me, that there is work being done by friction. And if we look on our formula sheet, in order to calculate the work done by friction, it's that minus force of friction times displacement. Is my force of friction 0.2? It says the coefficient of friction is 0.2. So is force of friction 0.2? No, that's the coefficient of friction. That's mu. So, like I said, in terms of like extra steps, here's where they kind of start. In order to calculate the force of friction, we take mu and we multiply it by our normal force. So we need to know what this thing is. We need to know our normal force. But do I know my normal force yet? Oh, no, we don't. You're right, we don't. But what's true about my gravitational force and my normal force in this particular problem? They're balanced, yeah. So my velocity is constant in the y direction. So, to add to our steps, we say F of g is equal to m times g. And the mass of this crate is 7. And that's times 9.8. Our F of g is equal to
16.6, I think.
Yeah, what do you think it is? 60.
8.6.
Yep, thank you. 68.6 newtons. This is 68.6 newtons. My gravitational force and my normal force are equal to one another because my forces are balanced. Therefore, my normal force also is 68.6. Now, I can calculate force of friction and say that's 0.2 times 68.6 times 0.2. Our force of friction is equal to 13.72 newtons. Now, we can use this force of friction, bless you, in our work done by friction. So our work done by friction is minus 13.72 times the 2.5 meters that friction acts over. So we multiply that by 2.5. And friction is going to remove negative 34.3 joules worth of energy. This is going to go here, and this is going to go there. Okay? Now, if we expand out our energy pieces, we, ME2 minus ME1, That's what delta ME means. Work in plus the work done by friction is equal to ME2 is PEG2 plus PEE2 plus KE2. That's ME2. Minus ME1, which is PEG1 plus PEE1 plus KE. We said that we have work in and work done by friction. Those have values. We've already calculated those two values. Now we go through and ask ourselves the same question we asked before Christmas break. Is there a height? Is there a compressed spring? Is it moving at location 2? Is there a height? Is there a compressed spring? Is it moving at location 1? And by doing this kind of thing in advance with V's and H's and spring stuff, should hopefully help us quickly answer those questions. Kind of hopefully forces us. We said at location 1 there was no height, there was no compressed spring, and it says it started at rest. At location 2, we said there was no height, horizontal, pushed horizontally. There was no mention of a spring, so we're left with KE2. Specifically, we're looking for the V2 within the KE2. Before I plug in numbers, I'm going to expand out KE2. And that's our final equation that we get before we start plugging numbers in. Start plugging our numbers in. We've already calculated work in to be positive 100. We've already calculated our work done by friction to be negative 34.3, which is equal to 1/2 7 V2 squared. So 100 minus 34.3 is 65, it's a positive, 65.7, which is equal to 3.5 V2 squared. Divide by 3.5, divide by 3.5. $18.77 is equal to V2 squared. Last step, take the square root of both sides. And we get a V2 of 4.33 meters per second. Unless I screwed this stuff up, which is possible, but let me know if I did. That's about as many steps as we could possibly have. Slight variations of this could be, it's had a V1. If we had a V1, that's not really that different, except for now we have a KE1. We could have H1 or an H2, which then slightly complicates the solving for force of friction, so. But again, that's about as many steps as we can really get with these type of problems. So if you're good with that, you're doing pretty well. Questions that I can answer about those two problems. Okay, next week Thursday, you're taking your final test of the semester. It is a unit test. It is not a semester-long summative test. There should be, I haven't actually finalized it, if you looked at it yet, but but there will be a concept portion, there will be a calculation portion. Some of the concept ideas that were asked last unit are still pertinent this unit. You know, questions like, how do you calculate the PEG, or what question do you ask yourself to determine if there's PEG? Those are the same kind of questions you have to ask yourself in both situations. Okay? Questions about, like, how do you determine work in, or determine if there is work in? Those are the same kind of questions. So concepts probably is not going to be a whole lot different. There'll be a few twists just from the standpoint of now we do have work in and we do have work done by friction. So, you have a progress quiz that I just passed out. I have two different answer sheets located in the back of the room. One, I think the one over on this side has question number 1, parts A, B, and C, and then the one on this one is question number 2. So, check your work as you go, or at the end, I guess that's up to you. But as you have questions, or if you have questions, please make sure you ask me, you ask someone, get the help you need, because next Thursday, we're taking a test, and this is a fairly common, these are fairly common calculations that you'll have to do in your test.